Okay, recording is on now. Welcome back, everybody, to Math 8680, January 22nd. And we have been talking about, well, supposedly combinatorial rings in the Kähler package, except we haven't seen a ring yet. We haven't seen the Kähler package yet. So hopefully we'll see a bit of that today. But I've been explaining to you some combinatorial problems that involve some geometry that lead to a sequence of numbers, and people ask questions about what can they say about these sequences of numbers, and eventually we'll see how some rings became relevant. So I was about to review this first set of numbers we were looking at last time, which was when we had points, in R to the D, and we looked at their convex hull, the convex polytope that they generate. We asked about their face numbers, the F vector, right? F of P was the sequence of numbers of faces in each dimension. And we defined what faces were, and we talked about historically what the motivating question that first came up about these, aside from things like Euler's formula, V minus E plus F equals 2 for three-dimensional polytopes. One of the more serious questions that arose is just how large can the F vector entry, so the number of I-dimensional faces, be if we fix the number of vertices is n? And it was motivated by linear programming. And Motzkin, who was someone who was interested in linear programming, he made his upper bound conjecture, which said that he thought if you look at d-dimensional polytopes with n vertices, that there is a family of them, the cyclic polytope CND, which we defined as the convex hull of any n points on this moment curve, t squared, t cubed up to t to the d. So it's a certain kind of twisting cube, excuse me, I was going to say twisted cubic, twisted degree d curve, d-dimensional space. And it's a way of picking somehow generic points, but they're not quite generic. They're sort of artfully chosen generic points in d-dimensional space. And Motzkin thought that their convex hull, which look like these pictures, like for the two-dimensional cyclic polytopes look like these polygons on the parabola, vertices on the parabola t squared. And the cyclic 3 polytopes, they have vertices on this twisted cubic curve, and they look like this kind of clamshell on a clamshell picture that I drew here with these top faces and these faces underneath that we can't see. And in higher dimensions, they're a little bit harder to picture, and we'll talk about, they have some interesting weird properties in higher dimensions, these cyclic polytopes. But Motzkin suggested that if you fix the number of vertices as n, like n is 6 here, they will maximize the number of zero-dimensional faces, one-dimensional faces, two-dimensional faces, and so on simultaneously. Okay. And we had talked about how in trying to prove this conjecture that these maximize the number of faces, one could use a certain trick or a reduction called pulling vertices to show that if you fix the number of vertices, like here I've got 6 vertices in this prism, you can always get rid of polytopes that don't have simplicial faces. If their faces aren't simplices, like in this case, it's a quadrangle, that's not a simplex. Two-dimensional simplices look like triangles. And so if it didn't have triangular faces, for example, in a three-dimensional case, you know there's going to be another polytope that has the same number of vertices, but more faces in every dimension. And you do this trick called pulling vertices. You pick a vertex and you kind of pull it out a little bit. And what it does is it triangulates faces that it was involved with. So it makes more triangles. And you can keep pulling the vertices. And once you've pulled all of the vertices, one can show, we'll talk about this later more precisely, that you get to a simplicial polytope, one whose all of his boundary faces are simplices, and which has the same number of vertices, but more faces than you began with. So one only has to look among these simplicial polytopes for the maximizers. And this was, somebody asked me about pulling afterwards in class. Here I I started with a two-dimensional polygon, and I showed how you pull a vertex a little bit. You move it outward a tiny amount using the normal vectors for the faces that it lies on. You add a little bit of those normal vectors, but you don't go past any of the hyperplanes defined by faces that it didn't lie on. That's how you pull correctly. Anyway, so that's the state where we were at, was this reduction to understanding the face numbers of simplicial polytopes, how big they could get. And we were about to talk about how Peter McMullen entered the picture with a bunch of great ideas that eventually get us to the rings. So that's where we're at. Any questions before we continue the story? And Sam asks, regarding the history, does the UBC say something directly about the simplex method? And you thought in theory simplex method does not work in polynomial time. That's right. Yeah, there are these interior point methods that do work in polynomial time, but simplex method, right, it will not. In fact, there are these specific examples that you can create called like Klee-Minty cubes, where basically any pivoting algorithm one has for the simplex method will take exponential time to go from a starting vertex to the optimal vertex. Yeah, so the UBC doesn't say anything, really good about the simplex method. In fact, it's a little bit disheartening.
Sorry, what does UBC stand for?
Upper bound conjecture, Motzkin's conjecture that the cyclic polytopes maximize all the face numbers for fixed numbers.
Oh, okay.
Yeah, great. Good. So let's start with the first of McMullen's key ideas that helped us. And so is a key idea of McMullen, Peter McMullen, this is, again, not Kurt McMullen. The F vector of a simplicial polytope is way too much information. It's really redundant and too big. So TMI, right? It's redundant, it's too big, and it's better to look at something called the H vector. So I'm going to tell you what this is. Better to use the H vector. Okay, so this is going to be H0, H1, H. It's going to have entries H0 through HD. I'm going to call it H of P. Maybe I'll call it H with an underbar of P. I don't know. I'll probably be inconsistent about this. And it's some invertible linear transformation of the F vector. So one can get from one to the other. And I'll tell you exactly what this invertible linear transformation is later. But I think I'm first going to show you just a quick way to compute it due to Stanley. Oops, transformation of, because it's a little faster. Computable, for example, we'll see many ways to do it. So I'll call this Stanley's triangle trick. It's going to look like Pascal's triangle. Okay, so here's how the Stanley's triangle trick works. You write the F vector entries. Remember, F started with F -1, was always a 1. That was counting the empty face. There's only one of those. And you're going to have F0, F1, dot, 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 up through FD-1. I'm not going to bother putting the FD, which was equal to a 1, right? FD was the whole polytope itself is the only D-dimensional face. But I do include the F-1 up here as a 1 and the F0 through FD-1. And then I put the other boundary of the triangle over here. I'm going to put a bunch of 1s. Then I'm going to draw a line here, and then I'm going to put a 1 here. And then we are going to get the entries of the H vector down here. H0. Okay, let me start drawing like triangular dots here. And then H1 and H2. Maybe I won't put the 2. The entry that ends up over here is going to be HD, dot, 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 like this. Okay, I need to do an example or else this doesn't make any sense. But let me also tell you the rule. The rule for computing in this triangle is you're always going to take the entry here, an x, and the entry here, and a y, and you're going to get this entry by subtracting y minus x. So it's, instead of like in Pascal's triangle where you add two things to get the one below it, here you subtract a couple of things to get the one below it. Let me do an example. Let's, in fact, let's do the example right here. Let's let d equal 3. Let me take the cyclic polytope 5, 3. Maybe I'll draw it in orange because I usually draw these things in orange. Okay, here we go. It's got these 5 vertices that lie on this t squared, t cubed curve. And then we saw how the facial structure looks. You've got these faces on top that you can see, and then there are faces on the bottom, edges on the bottom that we can't see. And here is its f vector is f negative 1, f0, f1, f2. And so we've got one negative 1 dimensional face for the empty set. We've got 5 vertices. We've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I get 9 right? Yeah, 9. I don't trust my notes anymore. And then the triangular faces on the boundary, 1, 2, 3 in the front, and then 3 in the back is 6. Okay. And so I'm going to use that to compute the h vector instead. So I put the 1, the 5, the 9, and the 6 up there. That's my f's. Okay. And then let me do the rest of the computation. So 1, 1, 1, 1. This is going to be my h down here. And I have to figure out these entries. Okay, so I take 5 minus 1 and I get a 4. I take 4 minus 1 and I get a 3. 3 minus 1 gives me a 2. Okay, so I've gotten a couple of h vector entries. What else happens here? The 9 minus 4 gives me a 5. The 5 minus 3 gives me a 2. And then that 6 minus 5 gives me the last h vector entry of a 1. Everybody see how I was computing my h from the triangle? And so this is h, the indexing is a little different than the f. It goes h0 through hd, whereas the f over here was going f negative 1 to fd minus 1, but it's the same number of entries. And I think you can see how you could recover by going backwards. If I put this as my input data and I drew these 1s up here, I could then recover bit by bit the f vector entry. So you can see that it's invertible. It's encoding the same information. Okay. Everybody clear on how that triangle trick went?
So you were saying that the f vector was too much information, but if the h vector is equivalent amount of information, how does that work exactly?
Yeah, good. Let's start seeing. First thing is, Alex, notice 2 equals 2 and 1 equals 1.
Yes.
And in general, I only need half of these numbers because it's palindromic. Yes, cool. That's the very first thing about it. Good. First of all, theorem, Dane-Somerville. All right, so this is the same Max Dane from the Dane invariant, Dane surgery, topologists, early 1900s. So for the dimension less than or equal to 5 case, he knew about certain equations among the f vector entries, and 1927, Somerville proved this in general. For simplicial polytopes, you have HI is equal to HD minus I. For simplicial D polytopes, D polytope means a D-dimensional polytope. HI of P is equal to HD minus I of P. And, you know, so of course you could just say for all I less than or equal to D over 2, but the point is it's true for all I. So you really only need half of the H vector entries. Okay, this is already some clue that H vector is looking better than F vector as a way of encoding this stuff. And so one thing I'll convince you later on when we talk about the formulas for these things, the top H, HD, is the reduced Euler characteristic of the boundary of the polytope. And yeah, so this is encoding Euler's formula. The fact that this thing is always a 1 and this thing is always a 1 when we have this polytope is really, that's our analog of V minus E plus F equals 2, Euler's formula. That's one of the equations. But the fact that H2 is equal to H1 is encoding more information about the fact that we've got the boundary of a polytope. There's more, and the fact that it's simplicial, that all the faces are simplices, is getting encoded in some of these other equalities. Okay, that's clue number 1. This is also, if one was really thinking ahead, if one had foresight, and you know, people were starting to think this way, the fact that it's a palindromic sequence of numbers starts to make it look like the Betti numbers of a compact-oriented manifold, for those who've seen Poincare duality in algebraic topology. And so maybe these are looking like the dimensions of some graded pieces in a ring, like a cohomology ring of a compact manifold. That's approximately right. Well, so we'll see later on, you know, why this was correct intuition. And this is the inkling that there's some rings getting involved. But let me not say too much more about that. Okay, second clue here, and this was more of McMullen's point. McMullen realized that Motzkin's upper bound conjecture, when you phrase it in terms of the H vector, it follows from showing this, and this is what McMullen showed. HI of P is just less than or equal to something pretty simple. It's a binomial coefficient. It is n minus d plus I minus 1 choose I. So that, what did Motzkin's conjecture? He says, do you take these particular kinds of polytopes and they've got more faces than anybody else does in any dimension, you know, if you fix the dimension, if you fix the dimension and fix the number of vertices. And McMullen's saying, what it's really saying is that simplicial polytopes, okay, so I should say for simplicial polytopes, D polytopes with n vertices, simplicial. That you have this inequality. That looks maybe like it might be more doable. And in fact, this is what he did via a Schelling argument. I'm not going to do it via a Schelling argument. We're going to do it via rings. And this is already suggesting something ring-like. In fact, Minnesota graduate students who've ever taken an oral exam from me, they might recognize this number right here. This is, why did I parenthesize the n minus d? This is looking like a multiset count. It's looking like the number of I cardinality multisets of an n minus d element set. Or, let me rephrase it, the number of degree I monomials when you've got n minus d variables. So let me say it this way. It's the dimension of a polynomial ring in n minus d variables in degree I. Oops, darn, I'm running out of space. Let's try this again. Shouldn't have made that equality so humongous. Okay, I put a subscript either. Polynomial ring in x1 through xn minus d. I've got n minus d variables it's a graded ring. There are homogeneous components. You can talk about polynomials that are homogeneous of degree I, and that's what I mean by this, is the polynomials that are homogeneous of degree I in n minus d variables. It has a basis given by the monomials that have a total of I variables in them, and there's this many of them. So this is an exam question that I often ask students. It's some kind of version of balls into boxes. Again, the fact that this is the biggest any ring that's generated by n minus d elements can get in degree I, that's the way that we're going to show this inequality. So again, it's starting to feel like maybe rings could become relevant. Everybody okay? All right. It's not clear why it's, why the UBC would be equivalent to this, but we will see later. That's true. Okay, here's some more things that happened after McMullen showed the upper bound conjecture by proving that inequality. He supposedly went to a pub and got a pint and sat down with a napkin, and he started thinking about like all of the things that people began to conjecture about the face numbers of simplicial polytopes, because there was started to be a lot of activity after his proof, and he was thinking through it. And in fact, one of the things that people started to conjecture is that not only are those HI entries palindromic, but they're non-negative and they're unimodal. So they're palindromic, they're symmetric, right? They read forwards and backwards. Let me write it like this: symmetric and unimodal, meaning they go up, H0 is less than or equal to H1. In the middle, right, at HD over 2, roughly, they reach a maximum and then they go back down to HD. So they go up, but then they go down. And because they're symmetric, that peak must be in the middle. That's what I mean by symmetric and unimodal. So people started to conjecture that this might be true. It was not obvious. He didn't know how to prove that. And it's not even true for the F vector. This is false. It turns out people figured out later for the F vector. It's not unimodal in general, even for simplicial polytopes. Okay, so again, this is part of the superiority of the H vector. But then he started putting all of this together, and he came up with his G conjecture. Okay, so this was rather audacious. He said he thought he could completely characterize what are the face numbers of all simplicial polytopes in any dimension. So this is called McMullen's G conjecture. I'll explain where the G comes from. So he says the face numbers f of p for simplicial polytopes let me say simplicial D polytopes, D-dimensional polytopes, are characterized by the following. What's true? Well, first of all, it's all phrased in terms of the H. So the HIs are integers. That's going to be clear. The Dane-Somerville equations, HI is equal to HD minus I, and then the most important one. He looked at these things, the differences. H0, which we know is a 1, right? the H1 minus H0, the H2 minus H1, the H3 minus H2. Remember, he thought these things were unimodal. People were starting to conjecture this. And so these should be non-negative integers. We only need to go up to the halfway point because then they start to repeat on the way back down. He called this thing the G vector. So he called this G0, G1, G2. And what he conjectured is that this sequence of numbers was giving us the dimensions of the homogeneous pieces in a graded ring that was generated in degree 1. So I'm going to write is the Hilbert function, but that's just saying the dimensions of the graded pieces. Dimensions of the homogeneous components. Homogeneous, abbreviated. Of a ring, maybe I'll even say a graded R algebra. That's just a ring whose constant, whose degree 0 part is a copy of the field R generated in degree 1. And okay, so this maybe doesn't sound like a friendly thing to say, but in fact, these Hilbert functions for rings that are generated in degree 1 had already been studied by Macaulay back in the early 20th century. And he had written down the inequalities that characterize the vectors, which can be the degrees, the dimensions of the degrees of a ring generated in degree 1. So this, in fact, is really a set of explicit inequalities on these H's. In particular, right, it shows that the H0 or the G0 has to be 1. And it definitely shows that these things, they're the dimensions of something, so they're greater than or equal to 0. It proves the unimodality in particular. So this G conjecture, this was as I said, rather audacious. It implied everything that people knew, or not knew, suspected at the time, and was trying to say, better yet, we ought to be able to just completely characterize what the face numbers of simplicial polytopes look like. Okay, so questions so far? There's like something in the chat. I probably missed it many minutes ago. What does it say?
Oh, I was just being silly. I'm sorry.
Supposedly this is written on a
at the
napkin
pub.
at a pub. I wish I could get that napkin.
Wow.
Yeah.
That's crazy.
By the way, I have seen Peter McMullen drink beer, and he can drink a lot of beer. Okay. So what happened? So he did this in 1971. Did I say what year it was? No, 1971.
Sorry. Actually, I did have a question. I was just trying to think about how to phrase it. So I guess the real part that makes the G conjecture hard is that the real trouble is finding out what this graded R algebra actually is.
Yeah, but we have hindsight. We're going to do it. I'm going to show you what it is. In fact, hopefully today I'm going to show you an example of one of these R algebras for C553. Yep. Good.
Looks like there's a couple more things in the chat also.
Oh, thank you, Alex. Excellent. Sasha says, so the Hilbert function is 0 above degree floor. Right, because it's this G vector. We only write down the G up to the halfway point, right? We only need half the entries in the H vector, And this G vector is half the length. It encodes the half the entries that we need. That's right. We don't write it after the top half. And Sam asked, I thought McMullen didn't know about the, right. So here's the thing. McMullen, I think he was, this is a good question actually, Sam, is how much was already in the air about graded algebras being relevant at the time? Because Stanley was writing about his proof of the upper bound conjecture after McMullen for simplicial spheres where you do need the rings. And so I think McMullen by 1971 was already aware that rings and their dimensions of the graded pieces were relevant. Yeah, but that's actually a good question. I should ask Stanley at some point whether that's true. Good. So let me tell you about then what happened. It kind of was unproven for about 8 years, 9 years. Around 1980, two things happened. On one side, Billera and Lee, so this was Carl Lee's thesis under Lou Billera. Yes, what they did is they constructed the simplicial polytope that you needed when you were given an F vector, an H vector, a G vector that satisfied McMullen's conditions, constructed quite cleverly. And this is a paper I've never read through completely, never fully understood it. I've had Lou Billera explain to me roughly the idea for this construction, but it's clever enough that I've never looked at it seriously. If somebody would want to give a talk about that paper, actually just some of the ideas, I think it would be useful. Constructed cleverly a simplicial polytope given the data, given, you know, F satisfying McMullen's conditions. And their construction starts with cyclic polytopes, but it kind of gets rid of faces sort of by pulling constructions. It does something very similar to the pulling construction, but actually to take away faces from the ones that achieve the upper bound, right? Since they have the largest number of faces, you should be getting rid of some of them in order to construct the rest of the simplicial polytopes F vectors. Okay. And around 1980, Stanley proved the other direction. He constructed the commutative rings that we need. Okay, so actually he constructed the rings that interpret the H vector and the G vector. From the simplicial polytope to show that they satisfy, to show G satisfies McMullen's conditions. And it's actually extremely well motivated. So this, I'm about to show you an example, but what I want to say before we get into the example, this ring or these rings are well motivated. And they, you know, come from a ring that interprets the H vector that satisfies this Kähler package, which I haven't told you what it is. And so that ring that satisfies the Kähler package, all right, we're going to learn a few more keywords before we start the example. So it's going to be a quotient of a Stanley-Riesner ring. We're going to start with a Stanley-Riesner ring. And he did not call them that. And we're going to mod out in the quotient by a certain linear system of parameters, a bunch of elements of degree 1, which get us down to a finite dimensional vector space. Okay. Everybody good for the moment?
Yeah, I have a question. Yeah, this might just stem from my lack of understanding about local rings, but if the quotient uh, so what you're saying is that from the ideal generated by these by this linear system, the quotient is finite. Would that make the Stanley Reasoner ring a local ring?
Yeah, so we're actually not going to deal with local rings at all, but graded rings in many ways behave like local rings. So there's a very strong analogy between when you have a graded ring, so you've got maybe a field in degree 1, and then you've got the positive degree elements. All the things of positive degree, you should think of that as being like the maximal ideal in a local ring. And everything is completely analogous if you think about it that way. So no local rings, but all graded rings here. Okay. Well, let's do it. I think we should get to our example. In fact, I realized that the example would be enough writing and enough potential for me to make calculation mistakes that I should prepare it. Here we go. Here's our example. As promised, I'm going to take d equals 3. I'm going to take p to be a familiar polytope. It's our cyclic polytope with 5 vertices in 3-dimensional space. We computed its f vector. We computed its h vector. And now the g vector, right, was supposed to be, you take h0 is just, excuse me, I already made a mistake. Look at that, I made a mistake there. That's supposed to say g0, g1. There are only 2 entries in the g vector, right? It's half the length, and it's the difference of the h vector entries. So this 1 is this 2 minus 1. Anybody good with why this is the g vector for this polytope? Okay. So what am I going to do? I'm going to give you a ring that interprets the f. It's also going to interpret the h. It's going to be a Stanley Reasoner ring. And I'm going to take a quotient to that Stanley Reasoner ring that's going to interpret the h even better, more naturally. And then I'm going to give you the ring that interprets the g. That's the plan. Are we ready? Questions before we do it? Here we go. What's a Stanley Reasoner ring? I need to start out with a simplicial complex. A simplicial complex is a bunch of simplices, and every time I've got a simplex, all of its faces are simplices, so it's closed under taking simplices, these lower dimensional simplices. And the simplicial complex I'm taking is the boundary complex. It's the boundary faces of this simplicial polytope. So all the triangles, all the edges, all the vertices, and the empty face, they are in the simplicial complex. I'll be more formal about this later, but let's not worry about it. It's got faces, which are simplices of various dimensions. There's a negative 1-dimensional face. There's one of those. There's 5 vertices that are labeled 1, 2, 3, 4, and 5. So there's 5 of those. There's these edges, the edge 1, 2, 1, 3, 1, 4, and so on. Notice there's a missing pair that's not an edge. The only thing that's not an edge is right there. You see the 2, 4? That goes through the interior of this polytope, right? That would be in the middle. It's not a boundary edge. So it's not in my simplicial complex, which is the boundary complex. Everybody see why I crossed out the 2, 4? Then there's the triangles like 1, 2, 3 and 1, 2, 5. Notice 1, 2, 4 is gone because, oh yeah, I mean, it contained this interior edge. 1, 2, 4 is definitely not a boundary triangle. I'm only allowed to have the triangles on the boundary. Okay. Also, like 2, 3, 4 contains 2, 4. 2, 4, 5 contains the 2, 4. They're not there. There's one more though, a little more subtle. It's 1, 3, 5. That would have been this triangle, and that's in the interior. That's not a boundary triangle. Right? You might want to stare at this picture a little bit. I claim the 1, 3, 5 is not a boundary triangle, not a boundary face. Okay. So in fact, in this story, it's important to know who are the minimal under inclusion non-faces. Who are the minimal subsets under inclusion that don't span boundary faces, because that's what we need in order to write down the Stanley-Reisner ring. Okay, so what's the Stanley-Reisner ring? I pick a field, and I'm calling it R of delta. Delta is my simplicial complex. I have a field, I have a simplicial complex. I form this ring. It's going to be a graded ring. It's going to have variables indexed by the vertices, because I had vertices 1, 2, 3, 4, 5. I have vertex variables x1, x2, x3, x4, x5. Okay, I start out with a polynomial ring. That's a nice graded ring. It's got degree 1 stuff, degree 2 stuff, you know, spanned by monomials of various degrees.
Should the list of faces include 4, 5?
Good question. Did it? No, I missed it. I thought I was saving myself from making errors. Thank you, Colin. Did I miss any others?
I think that's good.
Thanks.
Wait, hold on. Sorry. Oh, sorry. Sorry, I was confused. I thought Adi was saying that 4, 5 was not an edge, in which case 1, 4, 5 would also not be a face, but it is an edge. My bad.
Yeah. Good. Okay. So the Stanley-Reisner ring, what you do is you mod out, you quotient by all monomials that don't span faces. And in fact, all I did here is quotient by the minimal non-faces. I said x2, x4 is going to be 0, and x1, x3, x5 is 0. What that means is in this quotient ring, when you think about it as a vector space, the whole polynomial ring had a basis given by monomials. This quotient ring, it's going to have a basis given by monomials that are supported on faces of your simplicial complex. In this case, supported on boundary faces of my polytope. So the monomial 1 is fine. That's supported on the empty face. The variables, they're all fine. They still survive. They're supported on the vertices. x1 squared is supported on the vertex 1, x2 squared, x5 squared. They're all fine. They're all surviving. x1, x2, x4, x5, they're fine. But the monomial x2, x4 has been annihilated. It's 0 in the quotient. Okay. And when I look at the cubic things, x1 cubed is fine, supported on the vertex. x1, x2, x3 is fine. It's supported on the triangle 1, 2, 3, which is on the boundary. But x1, x3, x5 is 0 in this quotient. Okay, and so on. You know, I didn't do fourth degree, who's the basis, fifth degree, but you could write down the basis elements in any finite degree, and you could start computing the Hilbert series of this ring in the variable t. It's going to be a power series whose coefficient in front of t to the k just keeps track of what's the dimension of the kth homogeneous component, or the kth graded piece. I'll say both of those words and they mean the same thing. When I talk about a graded ring, I'll talk about the kth graded piece, the kth homogeneous component. They're the same thing. And I just want to keep track of the dimensions and make it the coefficient in front of t to the k. And I get some power series that starts here, 1 plus 5t plus 14t squared. You know, if we just start counting, there was 1 monomial here that survived, 5 here, 14 here. And I didn't even count the cubic ones. Everybody okay so far? Questions? Okay, this is painful to compute it this way. So let's come up with a better way to compute it, namely the f vector and the h vector. So I claim it's easy to write down the Hilbert series of a Stanley-Reisner ring. And in fact, it very succinctly is encoded by the f vector and the h vector for your simplicial complex. So we're going to start talking about f vector of a simplicial complex. Fi is the number of I-dimensional simplices. And then we do this transformation to the h vector, which is just those transformed coefficients. So the Hilbert series, I claim, is easy to write down. You take f-1, the 1, plus f0 times t over 1 minus t, f1 times t squared over 1 minus t squared, f2 times t cubed over 1 minus t cubed. In general, you put fi minus 1 in front of t to the I over 1 minus t to the I. And the reason is, we'll prove this later, but you might want to think about this yourself. what we're doing here, this t over 1 minus t is really t plus t squared plus t cubed. It's an infinite geometric series. And this is counting the contribution of, for example, the things that are supported on vertex 1, like x1, x1 squared, x1 cubed, dot, dot, dot. That contribution of the generating function for those powers of xi would be t over 1 minus t, and there's 5 vertices like that that contribute. Or what's going on with this t squared over 1 minus t squared? This is really the contribution of things that are supported on an edge, like vertex, an edge that has vertices i and j. You look at all the monomials whose support is exactly vertices i and j. There are 9 of them because that's the F vector entry. They each contribute this to the Hilbert series. This is an easy calculation. Trust me, we'll do it later, but you might want to think about it now in your spare time. Okay. So the F vector lets us write down the Hilbert series as this sum of kind of weird terms, but we could put them over a common denominator, right? These things all have denominators that are 1 minus t to powers, right? The biggest one is a 1 minus t cubed, and that 3 is the d from our dimension of our polytope. And when you put them over a common denominator, the polynomial on top you can check is the h vector. It's 1, 2, 2, 1 is its coefficients. Sorry, the polynomial on top has coefficients given by the h vector. And that's what the f to h transformation is really doing. It's taking this expression and rewriting it as this expression. That's the natural way to say it. Everybody okay so far?
I'm
Okay,
sorry,
cool.
this is silly, but
Yeah.
were you missing powers of t when you made the common denominator? Or am I missing like an algebra thing?
So, right, this one only had a 1 minus t, but when I put it over a
But-
common denominator, I have
Yeah.
to,
But should be like 5 times that times t.
oh, thank you. Yes, you're absolutely right, Esther. Sorry. There's a 5 times t, and I'm missing some powers of t, exactly as you said. Excuse me. Yeah, again, I thought I was saving myself some errors by doing it ahead of time, and I just made errors. Good. Everybody good? Okay. So, in fact, this thing, this 1 over 1 minus t cubed, that actually looks like it could be the Hilbert series of a polynomial ring in 3 degree 1 variables. I'm going to take these 3 elements, I'm going to call them theta 1, theta 2, theta 3, that are of degree 1 in my Stanley-Riesner ring. They actually do turn out to generate a little subalgebra that has 1 over 1 minus t cubed as its Hilbert series. That's not obvious, but it's going to be true. We'll see why later. And if I take that subalgebra generated by theta 1, theta 2, theta 3, let me call it R of theta, the whole Stanley-Riesner ring turns out to be a free module over that subalgebra, that subring. Sorry, when I say subring and subalgebra, same thing. No distinction in my world. And that's,
Sorry, how did you choose the 3 thetas?
yeah, absolutely. Great question. For the moment, very mysterious, but I'm going to go down the page and I'll show you why. Because we're going to learn exactly how you choose good choices of those thetas. I will show you which ones work and which ones don't. Yep. Okay. And now when I have R of the Stanley-Riesner ring as a free module over this subalgebra generated by the thetas, if I quotient by the ideal that the thetas generate, then this quotient ring is going to have a basis that interprets the H vector. So because it's a free module, we'll see why later. I haven't shown you this. There's some combinatorial commutative algebra. If I quotient by the generators for that subalgebra, take the ideal that they generate, this quotient ring, I did the calculation here. It's not too hard to show that it's got a basis 1, And then the variables x2 and x5, their images, these quadratic monomials, this cubic monomial. And when you look at it degree by degree, so this is degree 0, degree 1, degree 2, degree 3, its Hilbert series is just given by the h vector as coefficients in front of a polynomial. Okay. All right. We're running out of time. What I'm going to have to show you next time, so we interpreted, we just found a ring, this quotient, that interpreted the h vector. I'm going to show you how next time in that ring, I can pick a degree 1 element. Again, for the moment, mysteriously. Later it will be, I'll show you exactly how you pick it, such that when we quotient this ring by the ideal generated by that degree 1 element, it will interpret the G vector. So I have to take another thing of degree 1 to mod out by, and I will get a ring that interprets the G vector. That's the idea. But I'll do this computation more slowly next time. I don't want to go over by too much. Everybody okay? All right, questions before I turn off the recording, and then I'll be hanging out.
Yeah, so the main problem with the G conjecture was I believe it was finding a graded algebra that with all the right dimensions, and so I take it that this new quotient describing the G vector that wouldn't be that ring.
No, the one I'm showing you at the end there, I took the Stanley Reasoner ring, mod the thetas, and then mod this extra element L. That is the ring that interprets the G vector. With its,
Okay. So that ring is just straight up the solution.
yes. And we will prove this in general. We'll see how you get the thetas and how you get the L. Okay? I'm going to turn the recording off.